So as Uli said, my name is David Weitz. I'm a theoretical computer scientist, which means I deal with abstractions of computation. And before I tell you about abstractions that capture evolving scenarios, let me maybe quickly revisit our classic view of computation and kind of point out some glaring flaws for modern applications. So historically, the way we think about computation is the following black and white three-step image. We start by collecting our data, we feed it to some computer optimizes over this data and then spits out a solution which we use to maybe build a light rail near the campus. Okay, we're figuring out the technical stuff. So there's a few kind of glaring issues with this abstraction. Right. So a few issues with this abstraction. Well, first of all, this parenthetical single machine is increasingly becoming unrealistic for data sets that we consider. But even if you replace this one computer with a number of computers, I'd argue that this linear flow of computation is missing something that's kind of inherent to a lot of computational tasks we're faced with today. And the core reason is the abundance of evolving data. So here we have, a little hard to see with this resolution, but Lyft, Uber, and Get. And in all of these applications, data is not a historical artifact. It's an evolving construct, which is generated over time, say by users interacting with an app. This data is then fed to some central computers plural, and these have to quickly update their solution and externalize it to the users. Okay, so this morning I was telling a few of you my bike broke down on the way to my PCR test, so I needed to quickly get a cab to go get this test, and having an interface where it's okay, we'll solve this in an hour or 2 days is of course useless, right? So you need to quickly respond to changes to the input. Question from the audience? So in both kind of aspects of modern computation, which we addressed, both big data and evolving data, I'd argue that there's one underlying common challenge, which is uncertainty about the input. Right? In evolving data, we have to make our decisions based on only part of the data so far, because only part of it has been generated. And in massive data, where no single computer can actually store the entire input, well, every single one of these computers has to work with only parts, a partial view of the world. Okay, so there's different nice mathematical abstractions on how to deal with these types of problems. I'll mention a few. Online and dynamic algorithms deal with evolving data. Streaming algorithms deal with both evolving and massive data. And finally, distributed algorithms deal with one common approach to dealing with massive data. Okay, so here's where I come in. I've worked on all of these 4 models of computation. I've worked on online algorithms where you want to study the cost of knowing the future or not knowing the future. Dynamic algorithms where we study time approximation trade-offs in evolving data. Streaming algorithms where we study space approximation trade-offs in the same settings. And finally, distributed algorithms where we study the cost of locality of information. This last work is tied into some fundamental questions on routing and network coding. And if you're interested in these 2 last columns, ask me about these offline, because I'm going to not talk about these at all. And for the sake of coherence of the talk, I'll focus just on evolving algorithms for evolving data. And to make things a little more grounded, I'll tell you maybe 3 stories that kind of tie into these 4 highlighted papers. Okay, so just a quick recap. We're going to talk about evolving data. And before I tell you the outline of the talk, let me maybe quickly touch on 3 kind of motivating applications. Okay, so we'd already talked about ride hailing, where we want to pair up riders and drivers as they enter the marketplace quickly. Similarly, in online gaming, we want to pair up players of similar skills without waiting for too long between pairing up a player that logged into the system. And finally, in internet advertising, which we'll revisit shortly, we want to pair up ads and ad slots. And I'll just point out one commonality to all of these problems, which is their subject matter, which deals with pairing up entities. So agents and agents, items and agents, items and items. Okay, so we have a very simple abstraction of this, or a very well understood abstraction of this, which is a matching problem. So we have an undirected graph. Nodes correspond to entities, say gamers in an online gaming platform. Edges correspond to compatible pairs. So we could pair up these agents. And what we'd like to do, abstracting away quite a bit of the intricacies of these motivating applications, is compute a large match, a large subset of no disjoint edges. Okay, so here's, for example, the max matching here. And I'll point out this is a problem. I said this is a problem we understand well. For over half a century, we've had polynomial time algorithms for this problem. I'll point out that in the same seminal work of Edmonds, he actually introduced the class key, albeit informative. So in a section titled Digression, he says, this is what we should strive for when we talk about efficient algorithms. And if you'll allow me my own digression, I'll mention that the study of matching theory over the years has been influential for combinatorial optimization and approximation algorithms, etc., more broadly. So it's kind of good that the first problem we're looking at in the space of evolving data, or the core motivating problem nowadays, is one that is likely going to help us come up with some underlying approaches for these types of scenarios. Okay, so back from the digression. So as I said, this problem is polynomial time solvable. Unfortunately, this ties into this classic view of computation, which, as I said before, is not at all what we'll talk about today, and not what a lot of these motivating applications relate to. Okay, so this brings us to the topic of today. Today we're going to talk about matching in evolving graphs. I'll tell you 3 stories in this space that tie into my work. So the first story I'll tell you is about online matching and a resolution of a 30-year-old question in the space. Also kind of point out the recurring framework and just give you a little bit of a taste of things I like to do. And the second part of the talk, I'll tell you about online edge coloring, how this relates to matchings. And here I'll actually give you a bit of a more detailed view of kind of things, the way I tackle problems. Finally, in the last part of the talk, I'll have a bit of a thematic change. You can see also in the icon, but also in the subject matter. The first 2 stories related to online algorithms. The last one will talk about dynamic algorithms and recurring challenge in the dynamic algorithms literature, which I'll make a bit more concrete as we get to that part. Good. So that's kind of the roadmap for the talk. Let me also kind of give you a sense of the timeline here. So the first and last parts of the talk will be a little shorter, just give you kind of a sense of results and maybe a feeling for how things go. And the middle parts, I'll actually give you a bit more detail. So when we get to the end of the second part, don't worry, I'll probably not go over. So not go over. Questions at this point? Good. So let's dive in. So I'll tell you about online matching, and let me maybe revisit one of these motivating applications. I feel like the resolution here is not great. Anyway, before coming to Tel Aviv, imagine I'd never been here before, which is maybe a bit of a stretch. But what I like to do before visiting a city for the first time is type in to Google, things to do in the city, get a sense of what I can expect to do, in between meetings or in the evenings. So what Google will tell me after 1 point something seconds is here's a bunch of blue links. Here's a Wikipedia excerpt. Here's an excerpt from, I think, TripAdvisor. And also at the very bottom, it will give me an ad for Abu Hassan. Okay, which is perfect targeted advertising. And Israeli visiting Israel is, of course, starved for some good things. Okay, so what's going on behind the scene is when I search for something, Google generates an ad slot and decides which ad to display. So abstracting away quite a bit of this, what we have here is an instance of the online bipartite matching problem, where we have an unknown bipartite graph. One side of the graph is known ahead of time. So these are the advertisers, who we imagine have a budget of 1 ad. They can show 1 ad each. And on the left, we have the queries. So whenever a user performs a query, a node arrives with an edge to all the advertisers that are interested in showing this query. Okay, so maybe we assign. So what we have to do is assign immediately and irrevocably an add to this add. So maybe decide not to do so. So maybe we assign this third add to the query. Another query is performed. We assign a bit of a lag there. We assign this last advertiser to the query, and so on and so forth. And when we get to the third query, notice that we can no longer assign any adds to this query, because both advertisers have already depleted their budget. Okay, so this user will unfortunately not get an ad for arguably the best from the stage. Okay, and so on and so forth. And of course, our objective is to output large matching. And what this kind of simple example is supposed to illustrate is that while in the offline setting, when we know the entire graph, the problem is easy. In an online setting, approximation is inevitable. Okay, the fact that we didn't know that this node will be relevant to someone later on meant that we kind of depleted it too early.
So sorry to interrupt, but can you just please mute all the non-speakers? Thanks.
I don't think I can.
Малыш, я не слышу ничего.
And there's also AC. Can everyone at home hear me? Gil, Yossi? Vigorous head nods. Okay, thanks. Okay. Good. So back to regular scheduling. This problem was introduced by Kav Vazirani and Vazirani some 3 decades ago, quite a bit before internet advertising was relevant to anything. In particular, this is maybe 4 years before the first banner ad was even introduced, let alone the kind of dynamics I mentioned before. And what they showed in this work is that, without getting into the actual concrete numbers, is that randomization allows you to get a better approximation than deterministic algorithms can allow for. Okay, and this type of behavior where randomization allows for better approximation has been observed and proven for a number of generalizations of this problem, but all of this the kind of like bipartite flavor. We have a bipartite graph and nodes enter from one side of the graph. Okay, and the reason for these generalizations being studied so much is precisely this internet advertising motivation. But this, I guess, is a fair number of theorists in the room will all agree that there are other reasons to study theory than increasing Google's bottom line.
By the way,
yes.
This is like if you assume the randomization of the input.
If you assume randomization of the input, the problem becomes easy. The problem becomes easy. Sure. Yeah, but here I'm talking about randomization in the algorithm side.
Yeah, but in the randomization, there is randomization in the input, of course, right?
So the question is, what's the right modeling, right?
There's definitely. You said that people care about advertising. So
Sure.
People care about advertising.
They don't necessarily care as much about worst case guarantees. I'll give you that.
Yeah.
Still, we want to understand what we can do.
You said
Yeah. Fair enough. Other questions?
So when you say approximation, it's compared to best in hindsight?
Best in hindsight. So people here are familiar with the relevant jargon. We're talking about competitive ratio. I thought I'd stick to the term approximation during the talk to kind of make it more evocative of what we're talking about. Other questions? Perfect. So all I wanted to say here is that we know qualitative generalizations of this statement for all kinds of bipartite generalizations, but we know that there exist non-bipartite graphs out there. And there are applications where bipartite graphs are not the subject matter. And also, again, I'll remind you, this kind of problem, this original work predated its kind of motivating application by a good few years. Okay, so we can hope that generalizing in a way that's orthogonal to the way that this problem has been generalized, in particular to look at non-bipartite graphs, will underlie some future developments down the road. Okay, so this brings me to what was a central open question in the online algorithms and definitely the online matching literature, which was, does randomization help us in more general settings? So a little more verbosely, does randomization help us get a better approximation than any deterministic algorithm will allow for online matching and more general arrival models? And there's 2 different ways of parsing this. So let me briefly mention both of which generalize the model of Carp-et-al. So the first is vertex arrivals in general graphs. This was asked by Carp-et-al in their seminal work. Here we have nodes showing up one after another, together with edges to their previously arrived neighbors. So Danny was dozing off. Let me repeat the animation. Okay, so nodes show up one after another with edges to their previously. Perfect. Okay. Even more general than this is edge arrivals. This was asked by Aranya Mehta in his survey on online matching and ad allocation some 9 years ago. And here, as the name suggests, edges show up one after another, and you have to decide immediately and irrevocably, take it or leave it. Okay, so no, we can even do general graphs.
Okay.
Good. So in this case, what we have is this clear, ordering between the columns. There's the KVV model, which is easier than this, and this is possibly strictly. This is easier than this, or no harder at least. Good. So what did we show? So in joint work with collaborators at EPFL and Fox 19, Gamlat, Kapralov, Majoli, and Svensson, we answered both of these questions. Just realize this cursor. Good. So what did we show? So first we showed that randomized algorithms do not outperform deterministic algorithms under the most general setting of edge arrivals. And following up on Ishai's question, this impossibility result also holds in bipartite graphs. So even if you say, okay, I don't care about general graphs, I just care about edge arrivals and bipartite graphs, you still cannot beat cannot beat deterministic algorithms. Okay. On the other hand, where is this cursor coming from?
It's from there.
It's from there. Perfect, thank you. Good. On the other hand, we have positive results, and we show that the qualitative result of Carp-et-al also holds in general graphs. So in particular, randomized algorithms do outperform deterministic algorithms under vertex arrivals in general graphs.
So film one, although using edge arrivals, you can simulate vertex arrival, but it really says is that there exists a bad sequence
For edges, yeah.
That will cause the competitive ratio
Yeah.
to be
Exactly.
Exactly. Thanks.
So this holds for any problem. But however
This
you
holds-
define for every for any sort of graphs, or this is there's one graph or one sort of problem for which it does not have.
So
there's the generality of this normal.
good. So what this is saying, of course, on some inputs, randomization could possibly help you. I can cook up some examples without thinking too much. What this is saying is there is some family of inputs on which the best deterministic algorithm and the best randomized algorithm are the same.
But this might be trivial because the input might be very degenerated, and therefore there's nothing you can do. Like the empty graph, I don't know. So
Well,
definitely
the empty graph, you have a one approximation, right?
okay. So so definitely some very degenerated inputs, randomization could not help because there's a trivial solution. So I'm trying to
Sure. So I'm saying for a non-trivial input class. So okay, maybe I'll make things a bit more concrete. So deterministic algorithms can give you an approximation ratio of 1/2, kind of the most trivial thing you would think works. That's very easy to show that this is the best you could do deterministically. What this is saying is that there is some input on which you cannot get no randomized algorithm gets better than 1/2, or a family of inputs, a non-trivial family of inputs. No questions?
So, David, can you hear me?
Yeah, I do.
Sorry, Michal. Let me just, be rude and ask the question because I'm curious. So, but there, follow up on Iftach's question. There could be some ratio for which some graphs that have some approximation ratio for which randomization algorithms can actually outperform the deterministic one. It's only for the best ratio that you.
Right. The best worst case ratio you can get deterministically is no better than the best worst case ratio you can get. Oh, sorry, the other way around. The best worst case ratio you can get with a randomized algorithm is no better than the worst case ratio you can get deterministically. Is what this is saying.
Okay, thanks.
And Michal had another question?
I'm good.
Hi, Michal.
No, I'm good, thank you.
Oh, you're good? Okay.
Go ahead.
Good. So, okay, let me give you a little bit of a flavor of what goes in this theorem too, and then skip the next section. Okay, so at a high level, the algorithmic approach is one that many of you will recognize. I'm going to relax and round. So instead of solving the integral problem, where each edge is either in the matching or not, 1 or 0, I'll allow edges to be matched to a fractional extent. And what I'm going to do, so this is a wider space of algorithms. You can imagine you can get a better than deterministic, than integral deterministic algorithm, and you can. And what I'm going to do is I'm going to interpret these fractions as probabilities and use them to toss some coins in a correlated manner to get a distribution over matches. So far, fairly familiar algorithmic template. Let me kind of, instead of going into the details of the analysis, just kind of point out why it's surprising that this works. So when we want to round a fractional matching in general graphs, so edges have fractional values, every node has some of these fractions incident on it at most 1. This relaxation of the matching problem allows for 1.5 times larger solution than the best integral solution. Right? So if I assign a value of 1/2 to each edge, I can match 1.5 edges in this triangle, which of course means nothing for integral matchings. You need 2 to tango. So you can only match 2 nodes, you can only match 1 edge. So generally, if what you want to do is round one of these fractional matchings in a general graph, you're going to have to lose a factor of 1.5 in the approximation. And the best fractional online approximation is something like 0.6, or actually a bit less. 0.6 over 1.5 is less than 1/2, so it's strictly worse than the best deterministic algorithm. So what I'm saying here is that there's something of a surprise here, a factor here, because at least a priori, if I want to round one of these fractional matchings in a black box manner, then it seems that this is a very complicated way of getting a worse approximation than the kind of trivial deterministic algorithm. Okay, nonetheless, in our work, we show that we can round a particular fractional algorithm in a white box fashion while preserving most of its value. And in particular, getting to an approximation which is better than any deterministic algorithm can get. Okay, so I promise no serious details, but I'm happy to field any questions you may have at this point.
David, just to be sure, all graphs are unweighted, yes?
All graphs are unweighted, yeah.
What is the approximation ratio that you get? What's the number?
What's the number? It's qualitatively greater. It's qualitatively greater than 1/2. It's quantitatively. It's 1/2 plus some unspecified constant. I'm happy to say something like at least 1 over a billion. Not necessarily much lower. I mean, I'll say this right now. This is definitely not the right algorithm. It just says that randomization does bias something. Okay, so this is the positive algorithmic result here. Let me maybe switch gears and tell you about a different problem, the online edge calling problem. And here I'll try to give you a little bit more of a sense of actual techniques. Okay, so quick recap for those who haven't seen this before and also for those who have. And k edge coloring of a graph is an assignment of 1 of k colors to each edge of the graph, such that no vertex has 2 edges of the same color incident. So I kind of told you at the beginning of the talk, everything is matching, so what's going on? So if you think about this for a second, every color class is precisely a match. Right? No vertex has 2 red edges, no vertex has 2 blue edges, etc. So if I just look at the red subgraph, this is a match. Okay, so we can compress this definition quite a bit and say that a k edge coloring of a graph is a decomposition of the graph into k matchings. Let me mention a few places where this pops up, at least in offline settings. So Shannon studied this in the context of color coding wires. More generally, this pops up in a number of scheduling applications where we want to schedule 2 agent tasks. And colors kind of correspond to time slots. Let me maybe switch to an online setting where we'll see this relationship a bit more clear. So the application we'll talk about is switch scheduling in internet routers. And here what we have are n output ports on the right and input ports on the left. And what we'd like to do is send some packets from input to output ports. And I could just represent this with an edge. So if I have an edge between this input and this output port, I want to send a packet from one to the other. Unfortunately, these ports are fairly restricted pieces of machinery, and they can only receive or send 1 packet per timestamp. Okay. And so if we kind of color edges by the time at which they're sent, then if you think about this, then every one of these color classes is a matching. Right? Every one of the input ports and output ports can send or receive at most one packet per step. And so we can just color the edges by the transmission time, and this is precisely an edge color. Okay. And so what we have is that the number of colors we use is exactly the time, or maybe if we compress things a little bit, will be the time to transmit all these messages. Okay, so naturally we'd like to minimize this. So let me tell you a little bit about what's known about this problem. For this, I'm going to need, good. Let me quickly tell you what the dynamics are, just to be clear we're on the same page. So we'll have offline nodes on the right, online nodes on the left. And when an online node on the left arrives, we have to decide which colors to assign its edges immediately in real time. Okay, so we call it like so, and so on and so on. Okay, and again, we want to minimize the number of colors. So good. So let me tell you about what's known about this problem. I'm going to need two parameters on the right, a little bit hidden by Sivan's cursor. So we'll have n be the number of vertices and delta be the max degree. And as it turns out, the max degree is very, very important graph parameter when talking about edge colorings. It's definitely a lower bound. Right? We want every node of degree delta to see delta distinct colors. Otherwise, by pigeonhole principle, it has two edges of the same color. So let me plot number of colors used by number of algorithms as a function of this max degree. So first, the classic theorem of Vizing tells you that in general graphs, the right number of colors is either delta or delta plus 1. And an even older theorem of Koenig's tells you that in bipartite graphs, delta exactly is the right answer. What about online settings? So this is offline. This is what we should be shooting for if we could get it. In an online setting, it's not too hard to think of a kind of natural greedy algorithm. Just assign the lowest available color. It's easy to show this uses less than 2 delta colors, or basically 2 delta minus 1. And a natural question is, can you do better than this? This is 2 times too slow. But unfortunately, a work of Barnoy, Motwani, and Naom from 3 decades ago today states that well, no. Okay. And this is the title of this note. Okay, the greedy algorithm is optimal for online edge color. Okay, so at least I think this kind of ties into our question earlier about possibility results. We say that for any input you cannot do better, etc. In particular, it kind of begs the question: so is this plot just the right thing, and should this part of the talk be much shorter than I told you? Okay. However, as it turns out, the lower bound of Barnoy et al. Is only relevant in this thin strip on the left, where delta is less than logarithmic. Okay, so that's the only place where this is right. So basically, the way you should be thinking about this plot is you need 2 delta at the beginning, where delta is less than log, and then all this lower bound is saying is you can't get the right thing throughout. Okay, so let me maybe move this to the right. Good. So here's where we're at. Offline opt is delta. The kind of trivial algorithm uses twice as many colors, and the only lower bound we have is that we can't quite get delta. Okay. And so you might naturally ask, can you get close to delta when delta is super logarithmic? So to the right of this region where it seems like these lines are basically the same. Okay, so if you ask this, you wouldn't be the first to ask. Indeed, Barnoy et al. Conjecture that if delta is super logarithmic, you can essentially delta edge color your graph. You can color it with delta plus that lower delta colors. Okay, so what do we show? So in joint work with Ilan Cohen and Binghui Peng and Fox, also in Fox 19, we resolved this conjecture and show that indeed, if delta is super logarithmic, you can essentially delta edge color bipartite graphs in an online setting. So in the kind of dynamics I've mentioned earlier, this one-sided bipartite vertex line. Good. So let me tell you a little bit about maybe the high level, and then I'll drill down a tiny bit. So at a high level, our approach is a fairly natural one. We're going to run a number of online matching algorithms. Call the output of the first one, call it the red color class. Run another online matching algorithm. So this is the first online matching algorithm. So we killed off the red matching. We run an online matching algorithm on the remaining graph. We call this green matching, and so on and so forth. And then we get an edge color. Okay, so at least the way I've mentioned this seems, yes, this is the way I've defined edge colorings. This is what you should do, right? You should be peeling off matchings after matching. And so the real question is, what matchings should we be using? What online matching algorithm should we use? Okay. And to answer this question, we presented the following reduction. So what we showed in this work, and what we used in a number of follow-up works, is the following. If delta is super logarithmic, so the actual interesting regime, you can essentially delta edge color a graph so long as you have an online matching algorithm that matches each edge with probability roughly 1 over delta. So it matches each edge. This is kind of the highest uniform lower bound you could give for each edge to be matched, because at every point in time, I can only match one edge of a degree delta node. So the most I can guarantee all of its edges to be matched is 1 over delta. So I'm saying if you can do basically that, then you can essentially perfectly edge color and matching in an online sense. Okay, so let me not tell you too much about this reduction. Instead, I'd kind of like to focus on this. I will mention before that this reduction has proven quite useful for a number of generalizations of the model I'm talking to you about right now. This bipartite coloring with one-sided vertex arrivals. So in follow-up work with Wajc and Grandoni, we showed how to okay, sorry. So in joint work with Amin Saberi and ICAP of this year, we showed how to extend this to general graphs with vertex arrivals. Some recent work showed how to use the same kind of idea, the same reduction for edge arrivals, so the kind of most fine granularity. And they also showed how to use this for random order edge arrivals, which implies a qualitative result similar to joint work of mine with Wajc and Grandoni from Soda. Okay, if you didn't catch all that, all I'm saying is this seems to be a useful reduction. It's really not restricted to online settings. So if you like thinking about edge colorings and all of your favorite models of computation, this might be a useful tool for you too. Good. So let me tell you a little bit about this algorithm that will match each edge with probability roughly 1 over delta. So this is based on joint work with Ilan Cohen and Soda 18, where we gave precisely this kind of algorithm, an online matching algorithm that matches each edge with probability roughly 1 over delta. And before I go into the details here, let me kind of tell you what's the kind of takeaway, if you're looking for some nice technical takeaway from this talk for you. The key tool here is the theory of negative association. So this is a tool introduced by probabilists some 4 decades ago, but unfortunately not quite well known enough within at least some circles of theoretical computer science. I'd argue this is a very useful tool. If you want to learn more about this, see the primer on my website. And I'll mention that based on my work as well as this primer, this tool has become increasingly kind of popular in my neck of the woods. Okay, so in the online dynamic and streaming algorithms literature. Okay, so some of this is mine. I guess the color scheme is making it a little hard to see, but a lot of this is not. So people have been using this. Okay, so back to kind of proving this theorem number 5. So what I want to show is the following kind of algorithm. When an online node shows up, we want to pick one of its neighbors, so that each edge is matched with probability roughly 1 over delta. Now, if you think about this, so first of all, you can only match the edge IT if neighbor I is free, is not matched before T shows up. And so by a simple application of Bayes' law, this means that we want to match the edge IT when condition of I being free with probability 1 over delta over the probability that I is free. We might want to do something different based on the complete realization, but if I only condition on I being free, this is the probability I should be shooting for. So what we're going to do is try and match with exactly this probability whenever I is free, regardless of the rest of the state of the world. This will turn out to be impossible, but we'll kind of find a tweak around this thing. Okay, so here's the high-level approach. When online node T arrives, for all of its free neighbors, we'll compute the probability Pi from the previous slide, which is 1 over delta over the probability that I is free. Okay, so I computed this for I, j, and k. And what I'd like to do is have T match to I with probability Pi, to j with probability Pj, and k with probability Pk. Unfortunately, I can only match T once, right? So these probabilities better sum up to less than 1. Right? Otherwise, I'm violating maybe the third axiom of probability. Unfortunately, these probabilities can exceed 1. So what we're going to do is, instead of matching with probability exactly Pi, we'll normalize by the sum of the Pi's when necessary.
What do you mean by the probability that I is free?
The probability over the algorithm's randomness.
This is like the a priori.
The a priori probability that it's free.
Condition on anything?
Condition on nothing. Condition on absolutely nothing.
Like if T is 100, I'm saying
what's the probability?
Time 0, a time 100, but the probability that I is free.
Exactly.
So
No, it's fine. There's also a delicate point of how do I compute this, but let's not worry about this. But sure, it's a number. Good, thanks. Okay, so what I'm going to do is instead of matching with probability exactly pi, whenever the sum is greater than 1, I'll normalize that.
I'm not sure I understand, but so this is known in advance at time 0. This probability.
This is not known in advance. So based on the input so far and on the algorithm's specification, I can tell you what's the probability with the true match. If I want maybe say just an empirical estimation, I could just run the algorithm a bazillion times.
So it's you say, okay, I did something specific right now, but what would be the probability over all possible?
Exactly. So I'm not, yeah, exactly. I'm not conditioning on the realization of my randomness so far. I'm just saying, had I run this, infinitely many times, what fraction of the time would I have been?
So you might match two edges.
No. I'm going to, oh, so good. So I match, so think of this as a multinomial distribution over the mean. So I'll match I with probability Qi, J with probability J.
Nothing.
There could be a probability I do nothing if the sum of the PIs is strictly less than 1. That's fine. I
just give up on this.
Sure.
Yes. See how to calculate the efficiency of this probability?
The way I've defined the algorithm right now, yes, there's one extra invisible line that I'm not going to go into that gives me a closed form solution for this problem. And then it's very easy. Yeah. Well, this given that it's easy. But yeah, the denominator I can
Yes. Technically, you're projecting on the simple PIs, right?
Sure. Yeah.
It's a projection. Like the minimum is the QIs of the best approximation.
Yeah,
of
for sure.
PIs in a simple.
For sure. Okay, so remember what I want to convince you is that I match each edge here with probability roughly 1 over delta. So here's some quick intuition. So if the sum of the PIs is always less than 1, then this normalization is doing nothing. So Qi equals Pi. I'm matching exactly with probability Pi. So whenever I is free, I will match it with probability 1 over delta over the probability that I is free. If these terms cancel out, I get exactly 1 over delta. Okay, so in an ideal world where the sum is always less than 1, I'm happy. So I mean, it's not always the case, but something kind of similar is true. So in particular, the expectation of the sum is less than 1. Each of these PIs is 1 over delta in expectation. So I have at most delta of these PIs. So this is most 1. So if I can show that the sum of the PIs is concentrated around its mean, and in particular, most of the time it's not much larger than 1, then I'm happy. And in particular, I get something qualitatively close to this 1 over delta. I get this approximately 1 over delta. Good. So let me kind of remind you how we normally approach these things. We use something like Chernoff bounds and say that the sum of independent variables is concentrated. Pictorially, it looks something like this. There's a sum of many normalized sum of a number of independent variables. It kind of looks like a Gaussian. Chernoff bounds kind of estimates our probability of being far from them. Okay. Unfortunately for us, these PIs, which are just a linear scaled, a weighted version of the indicator of whether or not I is free right now, these are very much not independent. Okay, just to kind of briefly show you this, if you look at online node 1, if I tell you that J is no longer free, it's matched, that tells me that I is definitely free. Okay, so they're very, very much not independent. However, Chernoff bounds still apply in some dependent settings, and particularly if you have strong enough notions of negative correlation, then you still have Chernoff bounds. And I'll point out one of these, and for time, we'll try and also give you a bit of a flavor of one of these notions, which is negative association. Okay, so this was introduced by Joagdev and Poshan in the Annals of Statistics in '83. And what this intuitively says, so when we have variables x1 through x7, pick your two favorite subsets, A and B. And what this is saying is if subset A is large, under whatever measure of size that you want to think of, then B has to be small. If this is large, this is small. Okay, this is a little hand wavy, a little imprecise.
If x1, x2, x3 is 1, then the probability, what do you mean? Like,
no, so if it's 1, how do you mean?
No, if we're all assigned to 1, what do you mean large?
Good. Let me do something more precise. And it'll be good. So a little more formally, here's the definition. Hand waving is nice, so to give it some intuition is nice, but still. We say that these variables x1 through xn are negatively associated if for any two monotone increasing functions f and g that are determined by disjoint subsets of these variables, so f measures that these guys are large, g measures that, how large are these guys, then for any two such subsets and functions f and g, the correlation is negative. So if I tell you that f is large,
F itself is out. There's a real value function.
yeah, f is a real number. There's this terrible lag here. If f itself is large, conditional on f being large, then g has to be small. Okay, and let me give you a concrete example since you asked for it. So there's a nice example observed by Dubashi and Ranjan, and actually they attribute their very elegant proof to McDiarmid, which says if the x's are binary variables, either 0 or 1, and I tell you that their sum is always less than 1, then what does this say? If I tell you a function of these guys is large, then the 1 has to be somewhere here. It's not here, though. So this is small. Okay, that's a proof, basically. If you want to formalize it a bit, it's not much more work. Okay, so this is kind of a nice natural definition, but are there more involved distributions that satisfy this than this kind of toy example and maybe independent variables? And as it turns out, negative association has a number of useful closure properties. It's closed under under independent concatenation. It's closed under application of disjoint monotone functions. And using kind of simple distributions like this and these closure properties, you can prove that more elaborate distributions, for example, a number that kind of pop up in balls and bins scenarios, are negatively associated. And if you're interested, those of you who have a meeting later, I can show you maybe like a quick three line proofs of some classic results that required a lot of work without this machine.
David, can I ask a question?
Sure, Michal.
I can see how negative association helps you in bipartite matching, but it seems to me that in general graphs, you won't necessarily have this negative association.
Right. So that's absolutely right. And fortunately, right now we're talking about bipartite graphs. But you're right that in general graphs, I've yet to see a nice application of this machinery.
But I'm a bit confused. I thought you said that this result applies to general graphs.
No, so right now we're talking about online matching and bipartite graphs.
Oh, only bipartite. Okay, thanks.
Sure. Other questions? Perfect. So I'll point out some useful properties. So, okay, you can show that distributions are negatively associated, but why is it useful? So first, it implies Chernoff bounds almost immediately. I'm happy to show a one-line proof later. It applies a number of notions of negative correlation, says something about the convex ordering. It basically has a number of very useful properties that we kind of normally associate only with independent variables. So this is the end of the lesson. If you wanted to learn something nice today, this is it. Let me kind of go back to our algorithm we were trying to analyze. We want to argue that this algorithm matches each edge with probability roughly 1 over delta. And if you remember, our intuition was if we can show that the sum of these PIs are concentrated, then we're good. Now, given what I showed you in the previous slide, you might suspect that I'm going to tell you that these PIs are negatively associated. Unfortunately, that's not quite the case. But the next best thing is true. So what we show is that the conditional intermediate match choices are negatively associated. So what do I mean? Conditional on the realization so far. If I look at an indicator for T matched to I or J or K, well, I can only match T to at most one guy. So these are negatively associated by the 0-1 principle. So using this plus a simple inductive argument, what we can show is that these PIs satisfy a weaker condition, which nonetheless still implies concentration. In particular, if, okay, whatever. I won't go into details more. Okay, so if you follow the proof for high-level sketch as it is, that's great. If not, let me just kind of recap what we showed. There exists an online bipartite matching algorithm, matches each edge with probability roughly 1 over delta. The key tool is the theory of negative association. Somewhat popularized it over the years. If this has piqued your interest and you're curious about how this would be useful for your research, or if you have used this before, I'll point out that I'm transforming this primer into a survey. So if you do, a modern survey of applications of this tool. So if you do have some killer apps for this, please drop me a line. Okay, so that's all I wanted to tell you about online edge coloring. And I'll remind you, this part of the talk is short. Okay, so I'll tell you a quick thing. Yes, Sivan.
Just to make sure I understand, you never assume that edges or the online vertices can also be deleted. They're all.
Yeah, everything so far was incremental. This is an online.
It doesn't
setting.
model the ad situation so well. Right?
This actually, that's not the reason that this doesn't quite model ads so well. Realization is really incremental. Right? You search for something, this creates a new node.
Yeah, but
and this needs to be matched. Now you search for something else, this creates a new node. Nodes never get deleted.
David, I have a question. It seems that you rely on. Can you hear me?
Wait, just a second, Rani.
Okay,
it seems like Sivan's pulling rank.
If you assume that every offline vertex can be made once,
yeah.
If I move to something else, I don't see the ad anymore. Then that advertiser can place the ad on somebody else's website. Sure. So
it's fine. That node is still there. How's your vertex deleted? It just wasn't matched.
It was matched for a while. I saw the ad. Okay. Then I browse to something else.
The more,
but advertiser paid for.
You already paid for
it. Okay,
yeah.
no.
That's it.
You assume that the budget is one.
So the real problem is more general than this. I'll give you that. But we can talk about this. Rani, you had a question?
Oh yeah, he seemed to rely on the fact that delta is known in advance, right? So can you do something to handle online delta discovery? Say new colors become available once the max degree grows?
Perfect. Thanks for the question. So as we show in the same work in Fox 19, not knowing delta makes the problem strictly harder. And there's no algorithm with approximation better than E over E minus 1. So no algorithm using less than, say, 1.58 times delta colors. And we can also match this building on similar ideas to what I highlighted here. All right, thanks. Perfect. So unless there's more questions about the edge coloring, let me briefly tell you about dynamic algorithms and the challenges of adaptively changing data. So just to make sure we're changing the setting, now things will be both added and removed over time. So we start with an empty graph, and edges are added and deleted. So we discover that this pair is compatible. Now it's incompatible, compatible, incompatible. This edge, things are complicated. It's compatible, incompatible. We don't know what's going on with them. And what we'd like to do is maintain a large matching fast. Okay, and large, can be quantified, but we want some good approximation. And fast, in particular, we want something, more insightful than just recomputing a matching from scratch. Right? Max matching problem is in P. You could just recompute it at every point in time, but I've just added or removed an edge. Recomputing a matching sounds, I believe the technical term is bonkers. Okay, it sounds unreasonable to recompute. Okay, so I won't tell you about the literature on this work. I'll just kind of point out this has been something of a poster child of the dynamic algorithms literature in the last decade or so. Worked on by all of your favorite authors and all of your favorite venues. Let me just tell you one brief anecdote about one such paper by one of your favorite authors and one of your favorite venues. Okay, and to give you a bit of context, I'll tell you about what was known before and what kind of ensued from this work. Okay, so quick executive summary of all these 30-odd papers on the previous slide is that up until 2020, the best algorithms we had, the best time approximation trade-offs that we had, were all obtained by randomized algorithms, which unfortunately all require the somewhat restricting assumption, which is that the updates are generated in a non-adaptive fashion. Okay, so what do I mean? Rather than having someone interact with your algorithm, see what he did, and based on that decide what to do next, so someone wrote down a sequence of updates. Okay? And this is restrictive for a number of reasons. Basically, there are two reasons for which we care about dynamic algorithms. So first, sometimes the dynamic problem is exactly what you're trying to solve. You have maybe a user-facing application, maybe cabs, drivers turn on or turn off their apps. You still need to kind of match people, rematch people with someone new. Okay, and generally the way things go, right, is if a user finds that the solution is never to its liking, maybe this user will start using a different app, or maybe it'll change its behavior somehow. Okay, so the updates are very much adaptive. Another reason why this is problematic is that dynamic algorithms can speed up static algorithms. But in a lot of these kind of reductions from one static problem to another dynamic problem, we need the dynamic dynamic algorithm to be able to deal with adaptively changing inputs. I'm happy to elaborate on this later, but I don't want to go into too many details. Okay, so all I'm trying to say here is, this assumption is fine, basically, so long as you don't care about using this anywhere. Okay, so you kind of need to be able to deal with adaptive inputs, both for user-facing applications and to actually speed up other algorithms. Okay, so fittingly, the central question in the dynamic algorithms literature, which has seen some progress coming out of Tel Aviv, which I'll mention more later, is can we remove the non-adaptive updates assumption? Or specifically for the dynamic matching problem, can we obtain the same kind of bounds that we know how to achieve when we assume non-adaptive updates, even in the more restrictive adaptive update set? And I told you this part of the talk will be short, so I'll just cut to the chase. In single authored work of mine in Stock 20, I showed that we can essentially achieve all the previous state-of-the-art time approximation trade-offs for dynamic matching, but now under adaptive updates. Okay. I'll point out that this kind of wasn't the end of the implications here, so I give a general framework for rounding fractional matchings, and this has been used in follow-up subsequent works in the following Fox and Stock for, let's see, decremental settings and for weighted settings.
Is it similar kind of result the adversarial streaming model?
It's very similar to this adversarial streaming. It's the same kind of question, essentially.
And similar techniques as well?
The results here had fairly orthogonal techniques to what people have been using for both streaming, for a robust stream.
So there's no reduction.
There's no reduction, and there's no reduction. We're still working on building a kind of toolkit for how to develop these types of algorithms. I can say I'm working right now. There's a generalization of what's going on here, which is can get some new results out of this, but we don't have a black box way of going from one to the other. And actually, we know that this is generally impossible, as I'll mention later. Good. So I'll probably skip the actual high-level overview. Maybe I'll mention a few things. So we're still kind of rounding a fractional matching to get randomized algorithms. Here we're going to use, instead of using matchings to compute edge colorings, we'll use edge colorings to compute matchings. And kind of as an intermediate construct, we need some sparse subgraphs that still preserve the matching. And the analysis of the randomization in the middle step here, which gives us these sparsifiers, again, builds on negative association, which again, I can't advertise this enough. This is like the sleekest little tool I like. Good, so let me maybe recap. So we talked about three problems: the online matching problem, the online edge coloring problem, and dynamic matching versus adaptive adversaries or versus adaptively changing inputs. Let me now briefly look towards the future. Okay, lag here is really. Sorry? Sorry, what's green? The green is future. Oh yeah, this works in Hebrew. That's good. Good. So generally, what I'm excited about doing is expanding this theory of algorithms under uncertainty for all the various flavors I've mentioned. Let me tell you kind of three kind of main questions which I think are likely to be guiding questions in my research going forward. So the first is this notion of adaptivity and dynamic and other algorithms. As I mentioned, this dealing with adaptively changing inputs is key for a number of applications of algorithms in these evolving settings. And the question of whether or not randomization is useful, or generally if we can deal well with these adaptive changes, is a key question which we already have some kind of high-level answers to. So generally, we know that adaptive inputs make problems strictly harder. So in the sense that randomization maybe doesn't help. So we've known this for online algorithms for over a quarter century. Recently, work coming out of Tel Aviv and elsewhere has shown that for dynamic and streaming algorithms, there is actually a separation between what you can do with adaptively changing inputs and non-adaptively changing inputs. If you're wondering who of your colleagues works on this, so Chaim, Ishai, and Uri have been working on this. I'm not missing anyone here. But despite the fact that for at least some problems, the need to deal with adaptively changing inputs makes the problem strictly harder. I've shown that at least for one problem, or one central problem, dynamic matching, this is not the case. And so I'm really excited about finding more settings and kind of trying to characterize when randomization does help us, even in the face of adaptively changing inputs. Good, so that's question number one. Let me mention maybe a couple quick more. So I'll talk about real-time online algorithms. In online algorithms, we talk about the following model. We have input revealed incrementally, and decisions are made immediately and irrevocably. Unfortunately, the vast majority of work in the literature kind of ignores the running time. In the very strong sense, basically what we're saying is, it's not so much that we have to immediately make our choice. What we're saying is the next bit of the input will be revealed after we make our choice, regardless of how long you take. Which is nice when we're trying to kind of understand the cost of knowing the future, but a lot of problems that are online in nature, you need to make your decisions quickly. I mean, really quickly. Right? So say constant time. Okay, so this brings me to this high-level meta questions. What can online algorithms do quickly? Okay, and I'm particularly excited about this question because I think it's a great excuse to kind of marry two communities that I, well, match maybe is the word I should be using, two communities that I'm part of and like a lot, which is the online and dynamic algorithms literature. Right? Online algorithms deal a lot with making immediate and irrevocable choices, and dynamic algorithms talk exactly about real immediacy. So what you can and cannot do in, say, constant time or polylog time, et cetera, et cetera. Finally, let me mention one more high-level question, which is the instance optimality question. So in a lot of these models of computation on uncertainty that I study, the challenges of these uncertain scenarios result in some rather depressing, pessimistic worst-case guarantees. So maybe this ties into what Yiftach was asking earlier about input being adversarial or not adversarial. But then in all of these models, kind of the worst-case pathological instance tells you that the kind of worst-case guarantees you can give are fairly restricted. Good. So this has kind of motivated a rich literature on beyond worst-case analysis, trying to kind of say, okay, but I know that for my input, for my problem, the inputs look like blah, right? Look like this or look like that. And what this generally results in is either tailored algorithms for your favorite instance or tailored analysis for your favorite instance, which is fine, but somehow kind of misses the generality that we're used to and expect from algorithm design. And so kind of the holy grail here is to search for algorithms that are in some sense instance optimal. So instance by instance, this is the algorithm you should be running. So I have some recent results in this flavor for the distributed congest model with Hoypil and Wajc. I've been working on similar kind of questions in online and stochastic settings. I'm really excited about finding more such results where you can say, look, this is the algorithm you need to. I don't care about your input. If you care about having an estimate for how long it takes, fine. You can analyze my algorithm on your input, but this is the algorithm you should be analyzing, and this is the algorithm you should be running. Okay, so let me just almost conclude by thanking you for your time. I'll also thank all my collaborators on the work we saw earlier. This slide has kind of two goals. One is maybe to show you some of your favorite researchers. The second one is to just kind of illustrate that, as you can tell, I'm a fairly social collaborative researcher, and I'm really excited about seeing who's the next group of colleagues I'll be sharing, maybe not sharing an office, but sharing a building with and collaborating with more in person. And with that, let me thank you for it.
Questions?
Any questions?
Yeah, people at home?
I have a question.
Yes, Michal.
So what's the relation between this negative association and the negative correlation, say pairwise negative correlation?
Right, so negative association implies negative correlation, and there's fairly easy examples that show that the opposite is not true. Yeah, I don't know how much more in depth of an answer you want, but that's at least part of it. I can point out, okay, maybe let me say one thing for those of you who like thinking about more continuous distributions. Pairwise negative correlated Gaussians are negatively associated. That's some useful property for, I think, to some people.
So you're saying there are cases where
there are
correlation.
Yeah, there are distributions for which negative correlation already implies negative association.
Are there any
generally-
other
generally-
are there any other interesting examples where this happens?
Not off the top of my head.
Thanks.
Sorry.
Can you say a few words about what exactly are instance optimal algorithms?
Sure. So I can tell you for. I can tell you a little bit about this. This result for.
the instance of the.
Right. So okay. I mean, this is.
אם אתה יודע מה הבעיה, אתה יכול כבר לשלח לו את הפתרון.
So the problem is actually, you know, let me maybe take this offline. I think getting into the actual model specifics is maybe a bit much for you. Yeah. Okay. But broadly, what you should be thinking of is the silver bullet. This is the right. This is the tool for the task, whatever the specific task.
Okay.
But can you say something about what it is without an example? Just give a bit, like 2 more sentences about the instance
Sure.
optimality.
So generally, what I'd like to do is be able to say, here's the best algorithm among the class of algorithms, the relevant class of models, algorithms for the relevant model. So for distributed algorithms, I want to say my algorithm solves the problem and is the fastest among all the algorithms for this particular graph, for example.
אבל תמיד, מה שאני אמרתי תמיד נכון. האלגוריתם שנותן
את
התשובה הספציפית הוא אדיר.
Right. So instance optimal is a little, I mean, this is a little imprecise, really, for distributed algorithms. All we have
So there is a permutation on the input, or this is one?
Good. So the graph is known. The weights specifically are not known. So this is the technical jargon is universally optimal. So for instead of existential, in the sense that there exists some graph on which every algorithm needs to take some time, the same this algorithm is the best you could get in the whole universe of graphs.
Okay, thank you very much.
David, is there an easy example of the situation where you said that you have